Global technology conglomerates are deploying capital on a massive scale. By 2030, the cumulative investments required to fund artificial intelligence compute demand are projected to approach $2 trillion annually, as tech giants secure the GPU capacity necessary to dominate the digital landscape. This hardware concentration is restricted by geography. The United States and China collectively control approximately 90% of the world's advanced AI data center capacity, while the African continent currently hosts less than 1%. Under this centralized architecture, East Africa risks a status as a data consumer rather than a digital sovereign. This revenue projection for the Middle East and Africa AI data center market shows the scale of regional demand. The market is expected to expand from roughly $1.6 billion in 2024 to over $7.5 billion by 2030. Capturing that value through legacy infrastructure faces physical obstacles. East Africa lacks domestic semiconductor manufacturing, and importing critical components like random access memory is complicated by currency volatility and steep duties. These frictions make building centralized, Western-style hyperscale facilities economically inefficient. A solution is emerging through a shift in how artificial intelligence operates. The industry is moving from the training phase, the resource-heavy development of models, to the inference phase, where those models are applied to real-world data to generate value for the end user. These phases have different geographic requirements. While model training requires a monolithic concentration of silicon, inference can be highly decentralized. It favors localized processing power that responds instantly to a transaction or a device at the network edge. This transition lowers the financial barrier to entry. Emerging markets can capture the economic value of AI deployment without first constructing $100 million centralized training clusters. Instead, regional operators can deploy compact, self-contained microdata centers. These lean hardware configurations can be placed directly inside urban centers like Nairobi, Kigali, or Addis Ababa to provide immediate localized processing. Securing East Africa's digital future relies on embracing this decentralized architecture. By moving compute power to the edge, organizations can bypass legacy infrastructure hurdles and execute intelligent automation on their own soil. The current cloud model forces data generated in East Africa to travel thousands of kilometers. When a user queries an AI model, the request often routes via subsea cables to servers in Europe or North America and back, creating a delay of 150 to 200 milliseconds. This delay renders real-time applications unusable. An automated traffic grid or a hospital diagnostic system cannot wait a fifth of a second for a distant server to process a critical data point. Beyond latency, offshore routing exposes regional economies to systemic risks. The global subsea cable network is physically fragile, susceptible to sudden geopolitical or environmental disruption. In early 2024, the sinking of the commercial vessel Rubimar in the Red Sea saw its dragging anchor sever 3 vital undersea cables. This single incident disrupted 25% of all data traffic flowing between Asia, Africa, and Europe. These outages paralyze digital economies. Cable failures have blocked millions of users from mobile money transactions and government e-services, highlighting the danger of relying on offshore infrastructure for domestic operations that support trillions in daily transactions. This diagram shows the architecture required to bypass these vulnerabilities. By deploying a decentralized mesh of micro-data centers at the network edge, data processing stays within the continent, isolating local operations from global transit failures. Local edge routing slashes latency to sub-20 milliseconds. This speed makes real-time robotics and vehicle-to-everything communications viable by processing data within the same city where it is generated. This mesh network also enables graceful degradation. If one node experiences a hardware failure, the broader network automatically reroutes tasks to adjacent nodes, ensuring that public safety and financial systems remain operational. For enterprise leadership, moving compute to the edge is no longer just an optimization tactic. It is a requirement for disaster recovery and national business continuity. Traditional hyperscale centers operate on a high-consumption energy model. They burn vast amounts of electricity to power silicon, consuming even more power and fresh water to expel that waste heat into the atmosphere. Transposing this model to East Africa places a strain on regional power grids and municipal water supplies. A medium-sized data center can consume over 100 million gallons of water annually, which is unsustainable in regions facing acute water scarcity. Governments are responding to this resource drain with punitive regulations. In Ethiopia, the national utility recently overhauled its pricing policy to target high-energy computing, nearly doubling electricity rates for facilities tied to the national grid. To remain financially viable, high-performance AI infrastructure must be decoupled from municipal utilities and their associated tariff shocks. A functional alternative is the Green Edge Sovereign AI pilot proposed for Nairobi. It is engineered from first principles as an autonomous, 100% off-grid system. By combining a 40-kilowatt solar array with high-capacity battery storage, the compute core can operate entirely off-grid. This architecture ensures continuous uptime, regardless of localized load shedding or grid blackouts. Powering the node is only the first challenge. Modern AI chips generate intense thermal loads that must be managed without energy-intensive air conditioning or evaporative cooling towers. The engineering solution is direct liquid cooling, which circulates a dielectric fluid directly across the microchips and heat-generating components. Because liquids possess a thermal conductivity superior to air, this method captures up to 90% of the server heat. This allows micro data centers to operate efficiently in tropical climates, without the energy penalties of traditional cooling systems. Operational sovereignty is achieved by turning energy and thermal output from liabilities into highly controlled autonomous engineering constants. Circular energy economics offers a different approach to data center management. Intense server heat can be treated as a valuable, tradable commodity rather than hazardous waste. This flowchart shows how server heat is recovered. High-temperature fluid from the liquid cooling system is routed through heat exchangers, allowing the thermal energy to be piped into adjacent socioeconomic facilities. In the agricultural sector, this stable heat supply can power closed-loop greenhouses. This allows for the cultivation of high-value export-grade crops like vanilla and orchids, regardless of ambient temperature shifts. A second application replaces fossil fuels in the mechanical drying process for coffee and tea, which are East Africa's primary exports. Local agricultural cooperatives currently rely on expensive fuel or unreliable grid electricity to power the mechanical dryers needed for post-harvest processing, which eats directly into their profit margins. Empirical data demonstrates that integrating recovered data center heat into coffee drying reduces active fuel consumption by 13.9%. This system provides a return on investment with a payback period of less than 6 months. This symbiotic model lowers operational costs on both sides. The agricultural community receives free thermal energy, while the data center eliminates the need for energy-expensive chiller systems. By integrating digital infrastructure into the socio-economic fabric of the community, operators can neutralize the threat of local backlash over resource consumption. Legacy hyperscale centers are massive, highly conspicuous concrete bunkers. Their sheer scale and utility footprints often trigger restrictive municipal zoning, legally pushing them miles away from the urban centers where the compute power is actually needed. Because liquid-cooled microdata centers are compact and quiet, they can be seamlessly integrated into existing urban real estate. This camouflage doctrine allows multi-million-dollar AI nodes to sit exactly where latency is most critical. Commercial banks, hospitals, and luxury hotels can host these secured nodes deep inside their own buildings. This ensures that sensitive financial or medical data is processed locally and never touches the public internet. This decentralized presence aligns with a macro-regulatory trend. African governments are implementing strict data localization laws to assert control over their digital destinies. The AFCFTA Digital Trade Protocol mandates that high-value civic and financial data be processed locally. Relying on foreign hyperscale clouds subjects this data to foreign jurisdictions, compromising operational sovereignty. Building massive hyperscale facilities in every individual market is often economically unfeasible. A localized mesh of microdata centers provides the only practical way to fulfill data residency requirements across the continent. The financial profile of these assets is distinct. While a state-of-the-art net zero node requires roughly $385,000 in capital expenditure, its estimated asset value reaches approximately $2.8 million by meeting the specific security and sovereignty requirements of institutional clients. This model is further supported by regional fiscal policies. In special economic zones like Kenya's Konza Technopolis and Rwanda's Kigali Innovation City, investors benefit from 10-year tax holidays, 100% investment deductions, and hardware duty exemptions. For technology providers, deploying net zero off-grid nodes acts as a mechanism to capture enterprise market share. It offers clients impenetrable data sovereignty while immediately improving their corporate ESG standing. Capturing the regional AI market depends on moving past monolithic dependency. In an environment defined by physical transit risks and shifting regulations, an intelligent, sustainable edge network provides the infrastructure necessary to secure long-term digital sovereignty.